So there are two parts of the Newton method, and one part is really easy to remember, the other one a little bit less easy. And the easy to remember, unfortunately, is the one that you'll really care about in practice. That's the one how to implement it. You can easily rederive it whenever you need it. Okay. So the Newton method works if I have a convex objective function f, and I have a non-negative second derivative. Okay, so the second derivative here has all non-negative eigenvalues. So what I can always do is I can just make a Taylor expansion, right? And then I have some higher order terms. And I could just go and say, well, hey, let's just ignore those higher order terms. Locally, this function looks quadratic. So we just solve for delta. We minimize it. And we get this expression here. Okay. Let's actually derive this update. It's very straightforward, and you want, who has done this derivation before? Okay, then I guess we don't need to do it, because it's really just minimizing a quadratic function. Good. So the good thing is that essentially you just now, rather than doing a gradient descent, you rescale your gradient by the inverse Hessian. And what it effectively does is it undistorts your space in such a way that you're moving more directly towards the minimum. Now, the cool thing about this convergence analysis is that you actually have two regimes. Well, it's not so cool in the sense that initially the Newton method may not actually give you very fast convergence, but once you're close to optimality, you're going to get very, very fast convergence at that point. This is a property that we will have to contend with later on when we do interior point codes. So this is why I'm explaining you the regimes a little bit here. Basically, if we are far away from optimality, this is essentially as good or as bad as a gradient descent algorithm. Now, however, once we move close enough to optimality, then if your function is nice and twice differentiable, yada yada yada, then the quadratic approximation to it is going to be a pretty good thing, which means that actually if I minimize its quadratic approximation, I'm going to get very fast convergence. As a matter of fact, I'm going to get quadratic convergence. Good. So the point is that for some region around x star, and it's going to claim that's my minimum, I can come up with this expansion here. And it basically says that the first order Taylor expansion between x and x, between x star and x, expanded at the point x, is bounded by gamma times the distance between x star and x squared. So that's the assumption that I have to make at some point around optimality happens. Now let's actually go and expand this Newton update. So xn plus 1 minus x star. It's xn minus x star minus inverse Hessian times gradient. Now what I'm going to do is I'm going to sneak in the gradient at the origin. Well, which I can always do, right? It's 0, exactly. That's why I can sneak it in. So, at optimality. Now, if you look at that, well, that's simply, I can, unexpand my Taylor expansion here. Right? So, inverse Hessian squared, so I just pull that into x minus x star again. So this is basically our two derivatives, and here I'm going to multiply and divide by the rate.
You mean the part
So it actually would have to be the second derivative here. Now, if I do that, and well, this is then bounded Yeah, so this actually would have to be the sixth derivative.
Yeah.
So d squared sub x of a of xn. It's a typo. Right? So I can just multiply and divide this term by the sixth derivative. So that's it. Okay. Now we have that inverse Hessian here, and we have here a term modulo this typo, which looks, exactly like what we have there, right? That was exactly our assumption. Now this is gamma times, the squared distance from the optimal solution. So I plug this in here, and I get this. Well, this is cool. Because what I now have is that after one step, the distance is bounded by the squared distance times the inverse Hessian times some constant. So basically, this is one big fat constant here, and here's a squared term. Now, as soon as that product here is less than 1, I'm done. Because at that point, of course, the left-hand side term is going to be even smaller, and it's going to, sorry, as soon as this is less, as soon as this is less than 1 over that, I'm done. Because then things will immediately start converging to 0. And I get quadratic conversions.
As a norm or the inverse of Hessian, you mean the matrix norm?
Yes. Well, basically the largest eigenvalue. So you could probably plug in different norms here, and then you would have to plug in a different norm there. And maybe you can make some corresponding assumptions. So I'm quite sure some people have written papers about playing with different norms here. I'd be very surprised if nobody had. It's a very obvious thing to do. So effectively you have two different convergence regimes. So initially we get just the standard gradient descent outside this region. And then we have quadratic convergence inside. Now the nice thing is the Newton method is affine invariant. In other words, if I distort my space, it's going to converge as fast as the original updates. And that just follows immediately because my Hessian is now going to have the distortion on both ends, inverse, and here I'm going to multiply by that distortion again. If I remultiply here on both sides, I get the same update.
Newton's methods are the special case of the gradient descent.
So there is a case when Newton's method is a special case. Yes. It's a special case whenever the inverse, whenever the Hessian is the identity. But those are the really simple problems anyway. But in some cases, your Hessian may be rather benign. There are cases when...
No, even it's not identity, it's something dependent on xn, right?
Yes.
And it's gradient descent, we choose the
yes,
t to be that thing.
Yes, then it would be gradient descent. The other thing is that in some cases, it may be a good idea to do gradient descent initially until you get closer and then use the Newton method, or use some rather different optimization algorithm in the first place. So there, you may actually want to switch regimes between different things. Once you're close to optimality, the Newton method is really great for squeezing out that last bit of accuracy. But far away from optimality, it may not be very good. Just because far away from optimality, your quadratic approximation can be horrible. That's the main reason. So what really happens is, if we look at some standard convex function, and we have the wrong metric, then I get something that jitters around a lot. But then if I use the Newton method, it locally adapts to the curvature of the space, and this way I'm going to take an update step that points me much better into the optimal direction than what it would have otherwise. Now, sounds great, right? I mean, after all, it's the solution of all problems, right? Unfortunately, it's actually a really terrible method if I want to parallelize this. So, while it has a very good rate of convergence, it takes a few passes of the data, parallel aggregation of gradient Hessian, it's all straightforward. if I have a very high dimensional problem, this kills me, because the Hessian requires quadratic storage and requires cubic time to actually invert. So in other words, you can't really do it for any large interesting problems. Now you might say, well, yes, I've implemented my Hessian, Hessian aggregation, and I have a Newton method, and it works on large amounts of data. And people have written papers claiming amazing speed-ups of their optimization algorithms. Unfortunately, the fine print is, and we trained on 1 billion instances and 1,000 parameters, so to say. In other words, they have way too much data for the few parameters. And this is not an interesting setting. And unfortunately, you see this over and over again where people claim very fast algorithms, and they use it then in parameterizations where, yes, the algorithm is fast, but for realistic parameter settings, it becomes useless. And for whatever reason, this gets through too many refereeing stages. So I hope that when you're a referee, you're not going to let such papers through. Okay, I think this is about it for today, and next time we'll look at CG and